Okay, hello everyone. Um, we have a special guest with us today from Cranfield University in the UK. Geoff Neale or Dr. Geoff Neale has joined us. He's here for most of this week. However, 2 of those days later this week will be down in Sydney. The role of what we're meant to be achieving today and tomorrow is a bit of a workshop around high temperature composite materials and understanding how this university and Cranfield University can collaborate in the future on that topic. But Geoff has kindly offered to present to the Composites group and to UniSQ more broadly on the topics of research that Cranfield do, which is quite broad. Cranfield University, for those who don't know, is sort of essentially in the middle of England. It's what I would class as a rural setting campus, not that dissimilar to ours. But more importantly, the holy grail is what Cranfield is. Cranfield doesn't have any undergraduate students. It only has postgraduate teaching. So I can see a lot of people with a smile on their faces already sharpening up their CVs. But Cranfield is a beautiful university. I spent some time there myself whilst I was in the UK in my previous life. There are some fantastic academics there, Andrew Mills, Alex Skordos, and obviously Geoff as well. And I'll go through a bit of a background on Geoff to introduce him. Geoff is a Royal Academy of Engineering Research Fellow and lecturer in multifunctional composites at Cranfield. Geoff's area, which I'm sure he's going to go through in much more detail, Geoff's area is primarily around through thickness reinforced multifunctional composites. Now, most people would recognize through thickness as a structural tool, particularly for toughening and various other things. Geoff has a unique take on this. Geoff uses the through thickness reinforcement for sensing capabilities. So Geoff's area of particular interest are in thermoelectrics, EMI and self-healing. He did his undergraduate degree at Bristol and his PhD at Ulster under, was it Alistair? Alistair Micklehagger. Once again, Alistair is another well-known name in the UK, fantastic academic, and would have been a great supervisor. Geoff has a lot of collaborations with a lot of industry, which I'm sure he'll go through. I won't steal his thunder. He also supports a number of research organisations such as the NCC. I know he's engaged with SimComp up in the Nottingham. He knows very well of the AMC and various other centres, so I'm sure he'll go through all of those in his talk. He's interested in both structural and non-structural analysis of composites and how novel fabrication methods can be used to achieve this. I'm going to hand over to Geoff. Geoff, this is your stage for the next hour. Hopefully, can people keep their questions to the end? We'll keep 5 to 10 minutes at the end for questions, if that's all right, Geoff.
I'll keep a track of the time.
No problem. Over to you.
Right, so everybody should be able to hear me. I think I'm on. Yep. Perfect. Right, so I mean, I won't sort of do an introduction because Pete just did a fantastic one for me, so I'll jump straight into it. So the kind of way I've organized these slides today is a bit about Cranfield more generally, a bit about sort of what our overarching research themes look like and our research aims, and I'll sort of narrow down into what is done within the Composites and Advanced Materials Center, which is where I'm sort of based at Cranfield. Right, so about Cranfield University, and this is where I've got this nice video that'll give you a little overview. So I'm going to play that. Right, perfect. Yeah, the video is a bit marketing heavy, but it is quite nice. It's just show pictures and facilities and bits and bobs, which is why I do like it. Okay. Right, so just brief overviews of what happens at Cranfield. So, really, really good stats there. 1-to-5 academic ratio, alumni across 30 different countries internationally. 7th in the UK for engineering power. 8% of our research is world leading, and the sort of list goes on. And we really strive to have international collaborations, industrial collaborations, not only in the UK, but across Europe and the wider globe. So we like to say that we're the UK's applied research powerhouse. We do a lot of applied research, and that sort of focuses all the work that we do. So just to give you an idea of size, so we count 5,000 postgraduate students every year join us, and as Pete said, we don't have undergraduates, which is a kind of a blessing actually. 900 doctoral students every year, and 8,000 professionals attend CPD programs every year. So these are sort of short courses, and the way the teaching is set up within the university, it's set up so that modules run over the course of a week as an intensive module, and they're also marketed as short courses for industry professionals, so they can come along, do the course, which is a module for the week, and then go back to their normal working lives. So again, going back to some of the statistics, so REF in the UK is a research excellence framework, and this is basically how the government decides how much money each university gets for research. So what you want is a high REF score, with a large percentage of your research being world leading or internationally excellent. So that was from REF 2021. That was the last REF cycle, and the next REF cycle is in 2029. So we're gearing up for that. And what they do is they assess your a number of papers from each academic. They look at your research environment, lots of different things, and they give everybody a score basically. But at the time of the last REF, we were number 2 in the UK for per academic research income generation. So in terms of location, so there's London at the bottom there, and then you can see Oxford, Bedford, and then further along the right-hand side, which is blocked by the Zoom people, is, oops, let me just move that quickly, is Cambridge. I'm just trying to pull that down for a second. Perfect. Is Cambridge, and effectively this is the new, so the UK government has this strategy for what they're calling the Oxford-Cambridge supercluster, and the idea here is to link up all the universities that are on this arc. Universities, there's a lot of tech companies along this arc, and the idea is to sort of have a UK Silicon Valley in this sort of area. So there's lots of money being pumped into this. And if you think of some of the largest, tech companies, if you think of, the Red Bull, Formula One racing, Mercedes-Benz, they're all along this location, and Cranfield is nicely placed at the center of that. Another really interesting thing that we have, which not many people know about, is the fact that we have this global research airport, and we are based on an old RAF military base. So this is sort of around World War II, and then this expanded into the Cranfield College of Aeronautics and slowly became a university. So we do have our sort of global research airport, and you saw some pictures or videos in the video with our aircraft. So we have a Saab 340B where we host the National Flying Laboratory for the UK. So what that means is that every UK student that does a degree in aerospace, for their aeronautics course, they come and they fly in our aircraft. We do some fun barrel rolls and other bits and bobs, and then they sit and look at the screens and look at the sort of avionics data, and that's sort of the end of their degree learning, and we host that for the country. Also, loads of other work there. We have our Boeing 737 aircraft, which is not airworthy, but it's groundworthy, and we use this for sort of avionics tests, electronics, materials, that sort of thing. But this is kind of just to say that the airport is a key part of the infrastructure that we hold, and really pushes into lots of different areas, including smart manufacturing, advanced materials, and our hydrogen future, and I'll talk a bit more about that. So just leading up to some of the sort of big innovations or big works or big sort of aims of the university, I just want to talk a bit about hydrogen. And this is the HYPER project. So this is where it kind of started. This was a £10 million investment to develop a low carbon hydrogen production facility, which is on the Cranfield campus. You can see the 777 on the, it's not the 777, the 737 on the left over there. And this was funded by what was then the Department of Business, Energy and Industrial Strategy, BASE, which has now changed their name to DSIT or DESNES or something along these lines. But at the end of the day, this was the sort of first point on the hydrogen scale for us, looking at actually manufacturing hydrogen ourselves, high purity and with lower carbon emissions. So we sort of started off here from a hydrogen base, and then we moved into this project, which is called HYDEX, which you can actually see we have some Australian collaborators there. We have University of New South Wales was collaborating on this project, and this was really around building a hydrogen ecosystem around training, skills, development of new products, demonstrators, and sort of the whole ecosystem starting off. So this is kind of where the heritage we've come from the hydrogen point. And the reason I sort of throw this up here so early is because in terms of the university's key direction moving forward, hydrogen is a really big part of that. So what we have here is the Cranfield University campus, and I've highlighted here the spread of our hydrogen activity. So this is sort of the grand plan. It's all being built now. This is based on a £69 million investment from the UK government, along with large industry primes, so Airbus, Boeing, EasyJet, BA, and it's all about having the whole hydrogen ecosystem planned out for the future. So it's not just about the materials we need, it's not just about the skills that we need, but it's also how we're going to integrate this into future airports, future buses, future bus stops, airplanes. And you can see, the whole spread at the top. So on the left, you have Cranfield Aerospace Solutions, which developed one of the first hydrogen fuel cell aircraft. This is one of these firefighting vehicles. So how do you put out hydrogen fires, basically that side of thing. So from safety perspectives, of course, leading into aircraft maintenance and monitoring, transportation, hydrogen storage, so that's sort of toe winding on fuel cells. And it's a really big part of the university's vision. So the big main building is under construction at the moment. And what you can see here is that, there's a real plan for this to be, and this is the government funded, it's called a Cranfield Hydrogen Integration Incubator. And this is the government's plan for the hub of all hydrogen in the UK, looking at research across the complete sector. So, if you do have interest in this, there's probably nothing that we're not looking at, from sustainable aviation fuel and hydrogen fuel for aircraft, so from the propulsion side, materials, airport management, safety, it's the whole spectrum of everything hydrogen related. And it proves to be a really, really interesting couple of years for us at Cranfield. As well, there's a CDT, which is a Center for Doctoral Training on hydrogen and hydrogen-related activities, which will start next year with 20 students. So taking a step back, how does Cranfield sort of look? We're not very traditional in the way the university is organized. We are organized in what we call themes rather than sort of departments or faculties. Well, we now have a faculty because of a restructuring. But these themes have changed around recently. They've changed some names, they've swapped some things together, and they've added in sort of artificial intelligence and robotics sort of separately out. But it's basically the same. And these themes act like departments at conventional universities, but they sort of operate a bit like sort of individual sort of consulting platforms. And that's kind of how we work with our industry partners. So we sort of make it so that the focus of the work is focused towards that particular segment or industry. So I won't go through all of them, but I'll go through the ones that are probably the most relevant to the people here. And so the first theme we have is the aerospace theme. Obviously, Cranfield having a very big aerospace heritage, 70 different specialisms across our teaching, #1 in the UK in terms of ranking of study for postgraduate study, and loads of international students. Cranfield is a very international university, and 75% of our students across the board tend to not be from the UK. So the aerospace theme, as you would imagine, focuses on everything aerospace, from propulsion to bits of safety to aeronautics, space systems, that side of aspect of things. So the second theme is transport, and in the past it was separate. Now it's in with aerospace and aviation, but these are older slides, but effectively transport was more along the lines of how you manage airports, how you manage airlines, how you do sort of the management of the whole systems. And this is a Boeing 737. And next to it on the right, you can't really see it very much, is a building called DARTEC, which is a digital aviation sort of like a mock airport terminal of the future. And they use this to test the technology that you put in airports. So passport scanners, readers, face recognition, borderless entry technology, that sort of stuff, as well as houses the UK's only remote air traffic control tower. So there's no windows out. It's just in a room, and it runs itself for the most part based on AI, trying to sort of get more efficiency in the system there. Defense and security. The thing to note here is that our defense and security colleagues are not at the main Cranfield campus in Bedford. They're based in Shrivenham, which is in Oxfordshire. And the reason for that is because Cranfield runs the UK's Defence Academy. So we have a separate campus there where we run the UK's Defence Academy, and all the work there is protected behind the veil of government secrets and official sensitivities. Anything that happens in Shrivenham is the same level of standard of security clearance and all the rest of it that would happen within any government sort of defense facility. And the reason we have that is to do things where we think we sort of need to hide behind more security protocols. But a wide varying amount of research here, from materials to avionics to aerodynamics. There's not really one focus in terms of one area, but it's anything around the sort of defense and security theme, as well as obviously radio frequency, EMI, lots of work with like NATs and the air traffic controllers around this stuff as well. Energy and sustainability, I mentioned here as well, because there's a big push in the UK now behind energy and sustainability, especially with our focus on hydrogen, hydrogen energy storage and all the rest of it. So we have a big sort of energy and sustainability theme. Again, lots of different students from around the world. In the past, it used to be quite a lot of students from sub-Saharan Africa. The demographics changed quite a lot recently, but working a lot with sort of the nuclear energy sectors on fusion, fission, these sorts of things, wind energy, wind energy turbines, tidal energy, and this sort of thing. And then the last one I'll talk about is manufacturing materials, which is where I'm from. So I sit in the manufacturing materials theme, and it does what it says on the tin. We focus on manufacturing and materials. So we are really focused on looking at manufacturing methodologies, processes, digital manufacturing, twins, the material science, and it's that kind of spread of things. So it's an interesting sort of divide, because the aerospace and defense guys will sort of focus more on the non-manufacturing side of things. Whenever they need to make anything, then they come to us and we sort of do the actual manufacturing itself. So we're a bit more agnostic in terms of application, but we sort of do get around, and I'll show some slides that sort of highlight some of our main research interests. Okay, so the Composites and Advanced Materials Center is one of the 7 research centers within manufacturing and materials. And we have 6 main, 6 main academics, myself included on the top right there. But we have Samir Rahatikar on the bottom left, who focuses on sort of biomaterials, sustainable polymers, sustainable textiles, that sort of thing. Christoph Koziol is our head of center. His focus is more around nanomaterials, graphene, carbon nanotubes, that kind of nanomaterials. He's a chemist by trade. Then to the right of that is Alex Kordos, who is a process scientist, really focusing on manufacturing process science. David Eyre is more along the structural lines of things, big Airbus projects running at the moment on replacing landing gear with composite landing gear components. Myself focusing on multifunctionality through thickness reinforcement. And then at the bottom there, we have Eva, who focuses on elastomers, rubbers, these sorts of things. That's a picture of the center staff. That was from maybe towards the end of last year. It looks cold, so I'm assuming it was around Christmas. But yeah, the students aren't involved in this picture, unfortunately. But this is sort of the center, the main center staff. So 6 main academics, and then an army of postdocs, researchers, research fellows, and PhD students who unfortunately are not in the picture. But this just gives you a sense of sort of who we all are and what we look like. Okay. So Cranfield Composites, Advanced Materials Center. I know this slide is very aggressive, but it does give you a breadth of the sorts of organizations that we work with. Quite a wide range of people, from different universities to aerospace is kind of the bottom left down there, to automotive is kind of the middle bottom. On this sort of side, you have sort of the governmental and semi-governmental agencies and organizations. And then sort of up to the top right seems to be a big mix of people from across lots of different industries. But the spread is large. As I said, we're sector agnostic. We work with any sector that wants to work with us. These days, quite a lot on energy and defense. In the past, loads on automotive, even quite a lot now on marine, which is quite interesting, a completely different use case. But yeah, so this just gives you a nice view of everybody who we have. In terms of the spread of the sectors we sort of work with and the kinds of things, the kinds of materials we work with, it's quite diverse as well. Not so much on the civil aspect of things, but increasing nowadays. But from aircrafts to coatings, components, things for de-icing, things for material protection from environments, metals, loads of different sectors. So this is just to kind of give a view that we do spread ourselves quite widely across different areas. Right, now getting into the juicy bits. Advanced structure. So this is an old slide, a very old slide. And the reason I have it up here is to give an idea of what we've done in the past and sort of where we've come from, where we're going. In the past, the center really focused a lot on larger structures, work with BAE on drones and offshore wind turbines and early electric cars, new wing concepts, car structures, smart joints. I mean, these are all much larger structures and very sort of composites focused. And this is where the center sort of come from. And slowly over time, especially with the incorporation of our current head of center, who's really a chemist by trade, we've sort of diversified our materials focus quite drastically. So at the moment, again, this is an older slide, but I think it's still good for showing the spread. At the moment, we look at composite manufacture, high-performance composites, fire materials, process and structural monitoring, loads on the integration of metallics into composites, either using sort of dissimilar materials joining or through thickness reinforcement, which is kind of my area, recycling biomaterials and biopolymers, energy storage systems. This quite a different range. You can see how the center has changed its focus quite a lot. And what's really nice about the center is that we're all sort of left to chart our own paths in terms of what interests us and where we'd like to go. So all the academics have their sort of area and lead groups in that particular direction, which is really, really good for sort of us being able to fan out our skills. So of course, I'm going to start with my area of research, which is primarily through thickness reinforcement, hybridization, and multifunctionality. And as Pete kind of alluded to, there's been a lot of work on through thickness reinforcement in the past. Cranfield developing a lot of the Z pinning work in the 70s, 80s, 90s. And it's been done quite a lot. It works for the most part in terms of increasing your toughness. But now the question is, can we use it to embed some sort of sensible functionality in the material? So I've done a lot of work in the past around different materials, embedding them in different ways, but more recently looking at much larger bits of through thickness reinforcement. Why? The next slide will sort of give you an idea, but why? Whenever you want to transfer heat, for example, through a material, the cross-sectional area becomes a big component of this equation. So you need something with a large enough cross-sectional area to transfer the heat. Same thing with lightning strike. You need these larger areas to transfer the amount of energy without everything burning up. So we've done quite a lot of work in terms of changing the size of these reinforcements, using additive manufacturing to embed materials with one another. And this is really important when it comes to multi-material joining as well. And I'll show you some research outputs in a bit that sort of come to talk about this. But obviously as well, there's a lot of work on the modeling of this stuff, not only during processing, but in its actual performance. As you can imagine, you start to think, I put massive pins into composites. How have I destroyed the in-plane properties? And the answer is yes, there's a bit of, there is always going to be a loss, but you can't get something for nothing. You can get a decrease in your in-plane properties, but you get a material that transfers heat extremely well. So it depends on what you want. And a lot of the work here was done with JLR. So this is kind of looking at battery pack heat and stopping thermal runaway inside of the battery. So heat dissipation and this sort of thing, but also a lot of work with lightning strike in composite materials. So another big area for us is vitreous matrix composites. So for those of you who don't know, a vitromer is basically a method of modification of a thermoset resin, where you introduce what we call a disulfide bond, which is where you see the two sulfide bonds there. You introduce this disulfide bond, and what this does is it lets a thermoset material behave like a thermoplastic. So you can reprocess it. So it still has the same high TG, it still has the same high strength and stiffness that you would expect from a thermoset, but it can be reprocessed. And you can change, you can sort of tailor the chemical balance between the materials that you introduce, or between the polymer precursors, to allow for a tailoring of that reprocessing temperature quite narrowly. So you can go from 160 reprocessing temperature down to the negatives, if that's what you so desire. And this is sort of more on the material chemistry side of things, and this is really led mostly by my colleague Alex, who's done a lot of work in developing epoxy-based and benzoxazine-based vitromers. So again, you get the same properties of an epoxy, the same properties of a benzo, but you have reprocessability in the material. Another really nice key area of research that we like to show off is this work on layer by layer curing of composites. So the problem here being when you have really, really thick components, in an autoclave and an oven, you typically have large temperature overshoots, which are inefficient and might cause damage to the material. So we have developed, within the center, Alex has developed this method of layer by layer curing of the material, where you can sort of put a layer of the material down, cure it with laser or flash lamps, and then you come back and deposit another layer as well. So loads of process science here on the adhesion between the layers, getting everything to cure sensibly. So you don't take it all the way to full cure. You cure it to about 25% till it's stiff enough. And then you can sort of do a post-cure in the oven after, but you can vary that quite a lot. And loads of work obviously done on the process simulation of this as well. And this is one of these techniques that we really hope to carry over into ceramic matrix composites, which is a great area of collaboration I think we can have with UniSQ. But you can see, you can get really, really thick components. I didn't put a picture of the actual geometry. We have made this geometry that you see sort of curing on the left. So the top image is the normal curing cycle, and the bottom image is a process simulation of this sort of layer by layer curing process. We have made this in the lab. Takes half the time. The material properties are the same, much less temperature overshoot. And all in all, a really good process. We just have to work a bit more on dimensional tolerances, I would say, is the main issue when you have complex geometry around curves and that sort of stuff. I want to highlight as well our focus on more non-conventional or sort of, different types of materials. So I've spoken a bit about vitromers, but we do quite a lot with aerogels, for example, and there's a whole area of excellence that we are forming around carbonic materials. So our head of center, Christoph, is one of these people who's pioneered a lot of the graphene work in the UK recently. And this is around the manufacture of graphene and carbon nanotube, continuous carbon nanotubes and continuous graphene from cracked methane. So you take methane, heats up really, make it really hot, you make a plasma, and you crack the CH4 open, you get the carbon, and you get the hydrogen that you can use for energy. This process is already industrially available through a company that Christoph co-founded. It's called Levidian. I think I will mention them later. But they brand themselves as a nanosystems clean energy company, but essentially they sell these massive units where you can buy this thing. It comes in a shipping container. You plug it in, and you can get a machine that makes you graphene and green hydrogen, well, supposedly green hydrogen at the same time. But it's very good in terms of driving the price of graphene down significantly. And it is graphene in its original sense. It is made at that level. It's not sort of shaved graphite down that way. Multifunctional Z direction hybridization of composites. So this is kind of what my fellowship is around. So I spoke a bit earlier about me using through thickness reinforcement to embed sort of thermal electrical functionality, but the question is why? And we have some use cases that we're pushing forward on the moment with using this for de-icing, for sort of heating, mixing through thickness reinforcement and something like a vitrimer to get self-healing capability in the material, looking at self-sensing and inspection in the material as well. And the next slide, I'll sort of show why through thickness reinforcement has been so useful for us in terms of self-sensing. But this is basically, the way the sort of fellowship of the Royal Academy works is that I am funded by them to work 100% of my time on cultivating this area of research and sort of offshoots around it. And I'm not expected to do any teaching or anything that's not related to me forging a research path forward, which is absolutely great. So this is why I'm able to be here and do all this sort of fun stuff, because I have the full academic freedom to push in any direction I like, basically. So this was a project from, when did this end? This ended at the beginning of last year, called SEER. And it's just to show you why we really looked at starting developing these larger through thickness reinforcing elements. This project developed, side by side, a composite tool that would self-heat and sense on the inside. So what you have is, in the sort of in the big round picture, you have a fiber optic sensor which sits on the surface of the composite tooling. And when you put the fibers inside and the resin is flowing inside, it measures the refractive index to give you an idea of curing. It measures the flow rate of the resin inside, and of course, it measures the temperature. So on paper, this tool, this self-contained composite tool, which was used to make other composites, is supposed to be able to, well, it does, sort of self-monitor itself and make changes based on what it thinks it needs, based on a set of machine learning algorithms. So the key challenge from our side at Cranfield was these sensors are about 2 millimeters in diameter. How do you get them into the tooling? Because they have to be absolutely flush on the surface. They had to be perfectly straight within, I think it was a 5-degree tilt angle. And when I mean flush on the surface, it was something like 5 or 6 microns, because it needs to be able to touch the resin on the inside, otherwise you don't see anything. So lots of really, really strict design criteria. And they didn't want to drill into it because they were worried about losing the vacuum. So we decided to use through thickness sort of punching or through thickness reinforcement insertion to get these sensors inside of the composite, slowly parting the composite fibers. So you sort of had a bit of a compressive force of the fiber sort of pushing back against the center, keeping everything in place, and it was able to maintain its vacuum. This year project went really well. There's a number, I only have one publication there on it, but there's a number of other publications we have on the manufacturing, on the machine learning algorithms, and on the sensor itself, because all of these were completely new to the project. And so if you have interest in that, please do get in touch. But this was kind of my baby for 3 years when I first came to Cranfield, and it's pushed on. We had such good, that was an EU-funded project. We had such good outcomes from this project that we decided to push on to a new project. And this has started at the beginning of this year. So myself and Alex are the co-eyes on this for Cranfield. And it looks at, it's called Pleiades. And it looks at repairing of aerospace components, so thermoplastic, originally aerospace components with sensing capabilities inside of them, using induction heating. But then the idea is that we will translate this into vitrimers instead. So we start off with a thermoplastic just for proof of concept, make it all work. We are redeveloping the vitrimer chemistry to work for this and work for the sensible temperatures. And the final demonstrator will be a thermoset composite aerospace component that will be able to be disassembled, reassembled, at various points, which is the real point of this. So we're trying to get better assembly and disassembly aerospace components, and there's a use case there around structural health monitoring and de-icing, which is why the sensors are embedded. So the sensors from the last project I spoke about, SEER, have sort of evolved into this aspect of sensor work, because it was, I'll tell you, those sensor guys really struggled to make these sensors viable. So I think, you know, there was nothing off the shelf that could work for this. So this is kind of one of our newer projects, which, you know, has just started, and I have a PhD student who's looking at the vitrimer chemistry around this. So I mentioned bits on hydrogen and Levidian a bit earlier. So we have a project here around multifunctional graphene coatings for pipeline protection. So this is G-coat, and this, as I mentioned to Pete and Tris earlier, there's this push in the UK to replace all the sort of gas pipelines with hydrogen pipelines and pump hydrogen to people's houses instead, and you use that to heat your homes. No, regardless of how you feel about this, it's a good materials challenge for hydrogen leaking out through the sides. And we had a really nice project around graphene coating, so embedding graphene in the paint, basically. So you could just paint the interior of the pipes and the exterior if you wanted to, and it would stop the transmission of hydrogen through the coating walls. So lots there on hydrogen permeability. The Clean Hydrogen Innovation Program, again, a really nice project within our center, which again focuses on this link between manufacturing graphene and carbon nanotubes with green hydrogen. Lots of work again there with National Gas, Scottish Power, Southern Electric, and Levidian, of course, who are our big industrial partner on this. And again, this is about generating clean hydrogen, cleaner hydrogen for the future, as well as looking at the storage tank solutions for sort of type 5 and type 4 tanks. A really nice one, and unfortunately I'm not allowed to say the name of the company who is funding all of this, but this is a £5 million project on using graphene and carbon nanotubes that we can make in our own lab. And I'll show a bit around our kit, is the sort of next where I'm going. But it's about using the graphene and the CNTs that we make in our lab to make long continuous wires to replace copper wiring. So effectively, the idea is that if you can make this graphene cheaply, or you can make these CNTs cheaply, you can then spin it into wires, and it becomes a lot cheaper than copper to use, and the conductivity is a lot better. It doesn't short out, it doesn't wear out so easily, and you can use this in a range of different electrical applications. This is a lot of research has been going on for years. Our head of center, Christoph, has been working on this for a very, very long time, and it's now gotten to a really good industrial maturity stage where it's being embedded with a large Japanese electric company. As I said, a £4 million project that is turning out really, really well. And I think my last bit on research projects is around ceramic matrix composites. And that's why I'm here, really to talk about high temperature materials. So this project, the reason that I'm here is around this Accord project, which looks at ways that Cranfield and UniSQ can work around ceramic matrix composites research. But in parallel, we have two main projects running at this point, LC3, which is funded by UKRI, but also by HTMS. And this is around low-cost carbon composite manufacturing. So this is around modifying a bit, playing a bit with the chemistry as well as the process science to make the cost of the material sort of come down significantly. So can you have the same quality with a much shorter pyrolysis period, shorter pyrolysis times, cheaper materials as polymer precursors, etc. And can you get the same property? So, we sort of started off with a proof of concept with an MSc project, which is sort of what you're seeing the image to the left, which is, the green composite, the first infusion and the second infusion. And you can sort of see at the top right that it's a really good structure in terms of low porosity in the material, just by playing with the process science, which is quite nice. Layer by layer, pyrolysis of CMCs is another bit that I'm very passionate about. And it's about taking the layer by layer process that I spoke about a bit earlier and trying to extend that into the pyrolysis stage of the material. So can you effectively lay down a layer of material, cure it, pyrolyze it, and then go back and add another layer? And are you able to sinter this together sensibly with good interfaces? The question at the moment is, I don't know. We're trying it. The project has just started. So when we have a result, I'll let you know. But I mean, I think it's probably going to be quite difficult. And lots of lasers. So health and safety is a bit of a nightmare. Around this, around the CMC, the last one I'll talk about there is the bottom right. So this kind of ties back in with my work on through-thickness reinforcement. And this was the first trial of a bond between tungsten and a carbon-carbon composite. So it's not been trimmed yet, and it was just before I left, so I didn't really get a chance to trim it off. But effectively, in nuclear fusion reactors, what you have is a wall of tungsten inside. And behind that wall of tungsten, there's a wall of silicon carbide composite. And behind that, there is a molten salt that they use to cool it, a chloride salt or a lithium salt, something along these lines. The big problem they have is they can't bond the tungsten together with the silicon carbide, and the thermal gradients are something like 300 or 400 degrees. So what we're working on them with is multifaceted. So we've got, I think this year we have, 4 MSc projects with them, 4 MSc students, looking at this interface between the silicon carbide and this tungsten, using through-thickness reinforcement to better transfer the heat between the material as well as provide the adhesive bond. So what do you get effectively is when you run the simulations, the stresses are absolutely massive. They're gigapascal stresses, but they are compressive. So what you get is compression around the pins, which keeps everything in place, which is quite clever and quite useful. But also, what happens on the back surface when you have these high temperature corrosive salts running around? So there's lots of work on that. Other aspects there around material manufacturing, making that a bit cheaper or a bit easier, and quality control. So there's quite a lot there with the Atomic Energy Authority, and they're quite keen to collaborate more generally. They have loads of problems that they need to get solved. We've been saying fusion is in the next 10 years for the last 50 years, and they still haven't quite cracked it. So I mean, as materials engineers, we should have a good time with that. And then lastly, there we have a new CMC manufacturing facility. So we just invested in pyrolyzation furnaces that go up to 1,300, and sintering furnaces that go up to 2,200. Still quite small, half a meter, no, not even half a meter, quarter meter kind of size specimens. But the plan there, along with this micro CT and the mass spectroscopy, which we do have, the plan there is to approach national level funding for much larger facility, as it doesn't really exist in the UK. Actually, no, it does exist, but it's behind significant paywalls. So for academia, this becomes quite difficult. So the last thing I'll talk about are just a bit around our facilities, which I think could be quite useful and helpful to everybody sort of in the room and on the call. So we have a large thermorheological and mechanical analysis suite. So we call this TherMat. And we have quite a lot of the kit that you guys have here, with the addition of the laser flash analyzer, which measures thermal conductivity and diffusivity up to 1,200 degrees, as well as TGA, which separated out from the SDT, which goes, I think, to 900 degrees. So this facility was paid for by EPSRC, which is the Engineering and Physical Sciences Research Council in the UK. So it is effectively, on some level, open access to academic partners. So just keep that in mind if you want to access some of the stuff we do here. The Composites Manufacturing Lab is our main sort of composites area with hot presses and robotics, big autoclave. This sort of center robot is my robot, which is a tufting. It can do tufting and Z pinning of flat specimens like you see there, but also of large aerospace components. That's a nose cone from a fighter jet from a couple of years ago, where we were reinforcing the ply drops at the edge of stringers there, as well as the top right image being my Z pinning setup with all my foams and my ultrasonic hammer. You'll be hard pressed to find another Z pinning setup probably outside of us, and I think Bristol might still have one, but I think they might have. It might be very secretive. I haven't seen it, and I don't really trust that it's all that it's all good. But I'm very sure that mine works because the NCC comes to me fairly regularly to do stuff for them. Filament winding, not as impressive as the kit you have here. But we do have a sort of very simple pilot scale filament winder with a resin bath that we're doing a lot of work on. Again, we're really focused on process science in this kind of thing. So we're doing a lot of work here on trying to wind things like Vitramer resins onto mandrels, and then effectively trying to heat, reprocess, and take it back off in the same virgin fiber without breaking it, without having to do any reprocessing. So there's also it's kind of, I think we're calling it unmanufacturing now, but I mean I don't think that word is gonna hang around. But this is kind of the focus of our filament winding work. It really is around the process science of winding new material resin systems. Basically, that's kind of what we're focusing on. So not particularly exciting in terms of an industrial spin. A lot of work. Why is this flagging? Okay, a lot of work on hydrogen permeability. So we're in the beginnings. As I said, Cranfield has a big overarching point on hydrogen, and there will be, throughout the university, there will be liquid hydrogen testing facilities. There will be propulsion testing. There will be everything under the sun related to hydrogen. But for the moment, we have a nice little setup for hydrogen permeability. And the reason I've thrown it up here is because we have worked quite a lot with VersaPerm to make a lot of edits to the coding in the machine and to the way these sort of fix specimens in to make it a bit more applicable to composites, because I mean it's just a generic piece of kit. So we have done quite a lot of work with them. We sort of have a bit more of a bespoke, modified kit that we can do with composites, elastomas, paints, lots of different things. So it is a nice piece of kit from a hydrogen permeability perspective for small samples. I think this might be the last slide. Graphene and CNT reactors. So as I mentioned, we do manufacture our own CNTs and graphene, and we do have the facility for this. So that's it on the right-hand side. And basically, the diagram shows what you get is this carbon precursor, which is normally methane or some other off gas that's waste from some of the industry. That's the idea. You take it from somewhere you don't want it. And you heat this up into plasma, and then you sort of fire other gases at it to crack the methane molecules. And then what you get is this continuous off coming of CNTs or graphene. So you can kind of see in the image in the furnace that's moving, you can see it kind of looks a bit like candy floss. But that's how it sort of comes out. And these are single wall atoms of carbon that we can then wind into wires or whatever else, or grind it up if we need it as a powder. But that's sort of how it comes. It's sort of like blown candy floss straight from the furnace, which is quite interesting. So we get a lot of use out of this facility. It's quite bespoke, and there's been loads of work into the chemistry and the process science behind this. And effectively, we've got a lot of graphene that we would love to do something with. So if you have any ideas for that, that would also be great. All right, the last thing I'll talk about is at least I think it's the last thing, the Henry Royce Institute at Cranfield. So Henry Royce is a UK-wide network of research centers, each focusing on different sort of areas of material characterization and behavior. And what's quite lucky for us, especially in the landscape or the scope of CMCs, is that we have the Henry Royce Institute that looks at high temperature and extreme environment materials. So I've put a brief overview of some of the kit that we do have there, but then the website's a lot more detailed. But it is to say we can do, basically, corrosion, fatigue, lots of different environmental conditions at extremely high pressures, temperatures, high cycles, forced cooling, forced heating, large sort of heat fluxes in materials. So this facility is free to access for academia across the UK. So if you come through us, we can get access for you to the things in these facilities, and the government picks up the bill, which is the best part for everything, basically, for consumables as well. So it is a completely free to use open access facility for academia, and that is funded through the government that we host at Cranfield. So yeah, have a look on the website if there's anything particularly that might be of interest to you. So I think, yeah, that's definitely it from me. I know that was a bit long, but I hope I gave a nice overview of everything.